guys, welcome to my channel. This is the first module of our series on probability for exam B. In this model, we look at teaching concepts of probability which are relevant to understand the probability theory, and we are basically looking at the set theory here. At the end of this module, we would like to know the definition of a set, understand some basic terminologies and some basic tools we need in the set theory, and lastly, signed off with the De Morgan's law in the set theory. Please stay tuned. Alright guys, welcome back. Now, we will begin with the definition of a set. Now, a set is a well-defined collection of items. So any set of items which are well-defined, classified as sets. So for example, we can have a set of fruits, we have a set of natural numbers. Now, the definition of this collection for these numbers is natural numbers, so it's well defined, and we know the elements that form part of the natural numbers. Now, we define the collection of fruits also as a set because anything that comes up as a fruit forms a part of this set. Okay, now sets are usually denoted by capital letters, so many times set notations are with capital letters. So as we go on, you would see more of this coming up. Now, we would want to jump off to look at some terminologies which would be necessary for our discussions of probability theory and the set theory. The first thing we would want to look at is what an element is. So now your guess is as good as mine. Now an element would be all the possible outcomes of an experiment. Let's take for instance the toss of a coin, right? Now, or the flip of a coin. Now when we flip a coin, we have either a head on the coin or a tail on the coin. Now, these two possibilities are the outcomes we get from the coin flip. So we can classify head and tail as elements of the coin flip. So we define an element as a possible outcome of an experiment. In our case, we discussed the flipping of a coin as our experiment. The next thing we would want to look out for is what an event is. Now, an event is a collection of one or more outcomes. So with that same example of the coin flip, the collection of outcomes we have in there are heads or tails. So the collection with head and tail gives us an event in a sense. We can also consider the toss of a die, right? The toss of a die, right? When we say when we toss a die, we get an odd number. The odd numbers with the toss of the die form the event space for which we would have to consider. So we have the collection of all possible outcomes being an event. Okay. Now, we would also want to look at what sample space is. Now, the sample space is a collection of all possible outcomes. The collection of all possible outcomes. So, for instance, if we toss, in our case, we are using the toss of die, which will make much more sense. The die has 6 faces, and it has numbers from 1 to 6. Now, all those possible values on the face of a die form part of the sample space, because we have a collection of possible outcomes which are the numbers on the faces. Now, the sample space is denoted by S, right? Capital S. And the sample space is a set on its own. So for example, we have, right, for the toss of a die, right, we have the sample space being the set of all the numbers from 1 to 6, right? And this forms our sample space. For the case of coin toss, we have heads and tails forming the sample space. So for our coin toss, we have the sample space to be head and what? Tail. So that defines the sample space. Okay, a quick thing to note, we need a notation for elements. So let's say let A, right, be an element of the set B. A quick addition to what we have. Let A be an element of the set B. Then it can be denoted as follows: A is, right, and this is said to be, is read as a member of. So if A is an element of a given experiment, that given experiment gives us an event, then A is said to be a member of B. So that's the quick addition we have to make. Okay, now we also want to know what an empty set is. Now, an empty set is also a set, but in this case, from the name, we can all presume very well that this set has no element, right? So it's a set with no elements. A set with no elements is called an empty set, and it is denoted by either psi or an empty set with curly brackets, right? So it's either we have our symbol psi or two curly brackets to represent our empty set. Okay. One other very useful terminology would be the use of subsets, right? Okay. Now let's consider any two sets. Let's consider two sets, say D and E, right? Now we can say that D is a subset of E if all elements of D are found in E. Right, so if all elements of D are found in E, then we say that D is a subset of E. So there are two interesting things we would need to know under this heading of subsets, right? There are two kinds of subsets we would need to know, right? And this is very interesting. Would have to know them. Now the first of its kind is the improper subset, right? And it is denoted by the symbol here with a dash underneath. Now let's consider two events A and B, right? A is an improper subset of B, right? If all the elements of A are in B, and also, right, and also the number of elements in A is equal to the number of elements in B, right? So there's this possibility that all the elements in A are in B. Then we consider A as an improper subset of B. Now we have the second one being the proper subset, right? The proper subset. Now the proper subset is denoted by our symbol here. Sorry guys, our symbol here, and we are still under the consideration of this A and B, right? Now A is a proper subset of B if all elements of A are in B and the number of elements in A, right, are not equal to the number of elements in B. Alright, so B is a greater, right, it's a greater set than A, and all elements of A are found in B. So, right, we can make this more formal and say number of items in B is greater of number of items in A. Then we can say that A is a proper subset of B. Alright. Now, the next thing we would also want to know is the use of the Venn diagram, right? Now, the Venn diagram is a diagram that actually helps us get relationships between two or more sets, right? It helps us tell the relationship between two or more sets. Formally, we can define this as a diagram showing the relationship between finite number of sets, and it's very useful in our probabilities. So we can see diagrams of this form, right? With two sets in there, A and B, right? And this is showing us the relationship between two sets. Now, this here is what we call a Venn diagram. It's a diagram to show the relationship between set A and set B, right? So it could be three sets or more. This is just a diagram to show the relationship between the sets. Talking about the Venn diagram, we'll look at very interesting concepts under that and our representation of the set, right? So we'll also look at the union of a set, right? Right, the union of a set is the set of all elements that are contained in at least one of the sets, right? So we consider two sets A. We have 2, 3, 4, and 5. We consider set B. We have 6, 7, 8, and 3, right? Now, we would get to know the union of these two, right, is the set where we have all the elements and they should appear at least in one of these two sets. The union is denoted by value U. It's denoted a cup, the symbol cup. So if we want to find the union of A and B, right, we have the set with values 2, 3, 4, 5, 6, 7, and 8, right? So at least we have three appearing 2 times here. We have it in set A and set B, so it appears at least once, and we called it once in our set. So that's the basic concept of the union of sets. This can happen for more than one set, more than 2 sets. Yeah, so that is basically it for our union. Now, another interesting concept we should also know is the intersection of sets, right? Now, the intersection of sets is the set of elements that are common to any number of sets, right? The set of elements that are common for each set. So if we have any set of numbers, sets, so referring to the set above, A and B, A intersection B, right? Sorry, it is denoted by our cap here. Now A intersection B now becomes whatever element is in A and also in B, and we can see that it's only 3 that forms part of the set. So the set of intersections is 3. This is also one thing we would want to know. Okay, next thing we would look at is the difference of sets. Now, the difference of sets, right, is a set containing all elements that are in one set and not in another. So for sets A and B, right, the difference of sets denoted by A minus B, right, is the set of elements, right, in A and not in B. We get it. So for example, if we have the same set as we have earlier, A minus B, then A minus B is 2, 4, and 5, excluding 3 because the set B doesn't have the elements 2, 4, 5, and that gives us the difference in sets. Okay. Also, we would also want to know what mutually exclusive events are. Alright, so 2 events M and N are said to be mutually exclusive if they cannot occur at the same time. So M and N are mutually exclusive if they cannot occur at the same time. Right, so from the name, they are told to, we say they are mutually exclusive. Now, mutually exclusive events in set theory are represented this way. So if we have M intersection N, then it is a null set. So they don't have any common element, right, between them. Okay, so that sums up what mutually exclusive events are. Now, when we see mutually exclusive events, we have another concept that comes in mind, and that is the concept of having disjoint sets. So mutually exclusive events are disjoint sets. Okay, then the last thing, which would be very relevant to probability theory, will be to know what the complement of a set is. Right, now the complement of a set is the set containing all the elements that are not in the set but are in the sample space. Okay, so they are not present in the set under consideration, but are in the sample space, right? So it is usually denoted by, right, by an inverted comma on the top, or you sometimes have a bar over a set. So for say set A, right, A bar or A, right, represents the complement of the set. So elements of the complement are found in the sample space, but not in the given set under consideration. Okay. So this completes the second phase of our study, and we would like to quickly look at an example which will help us better understand this whole concept. Okay, so suppose we roll a 6-face die once. You are given A in the event is the event where we roll an odd number. B is the event where we roll an even number. C is the event where we roll a number divisible by 3. And D is the event where we roll a number greater than 6. So we would like to do some set notations here, right, which will help us. First, take a quick pause on this video and try and see whether you can put in some effort in putting down this sets. Okay, so I guess we've been able to write down some things for the set. Okay, so now the first one says we have the event of rolling an odd number. So A is the event of rolling the odd number for the 6-sided. So to help us better see what we are doing, we can first write the sample space from the test, which is the set of numbers from 1 to 6. Okay, and also event A is odd numbers. So odd numbers in the set are 3, 1, 3, and 5. The second one says even numbers, right? Even numbers are 2, 4, and 5. The third one tells us to find the set of numbers which are divisible by 3. And we know it's 3 and 6 which are divisible by 3 in the set. And also D is the set of numbers which are greater than 6, and we have no number greater than 6. So D is an empty set. So if we are asked to find the intersection, we are asked to find the complement of A. The complement of A will give us all the values in the sample space which are not in the set. We have 2, 4, and 5, right, which are not in the set. So we can perform all the other operations accordingly to the set. Now we lastly want to look at the very crucial part, which is the De Morgan's law. The very first bit are basic things we need for our probability theory. Now, the De Morgan law is a very crucial part of the probability theory, and it's based on the idea of complement, right? The idea of complement. So there are two statements under the De Morgan's law. The first of it is for any two events A, for any two events A and B, A intersection B complement is the same as having A complement union B complement, and 2, A union B complement is the same as having A complement intersection B complement. So this is statements made by the De Morgan's law. We can better view this in a Venn diagram and see how best we understand. So let's say we have a Venn diagram, right? With events A and B. This represents our sample space. Now, we know A intersection B, right? From that Venn diagram is what is common to both of them. And from here, we can see this part of the set represents our intersection, right? And this is common to both of the sets. Now, if we find the complement thereof, right? The complement of it is the region in red, right? The region in red is A complement union B, A complement A intersection B complement. And you can see from what is here that if we find the complement of the intersection, right, then it is pretty interesting to note that the whole region here, right, all the red region forms part of this complement. Then if we find the complement of A, it is the region of B, and the region here, let's say this region is C, right? The region of B and B, this region of B, right? And this region of C form this region of B, and this region of C form the complement of A. Also, the complement of B is this region of A and the region of C. So finding the union actually confirms our assertion that A union B and confirms that De Morgan's law. The same happens for A union B complement, which is A complement intersection B complement, and that is the outer region of C. So that is the basic law of De Morgan. This law would be used further in our further models, and would have a better appreciation of it. Thank you so much for listening. If you are new here, please hit the like button and subscribe for me so we can reach more people as we study probability to pass the exam P. Thank you so much.